Gated latches and conditional transparency. Latches are designed to be transparent. That is, input signal changes cause immediate changes in output. Additional logic can be added to a simple transparent latch to make it non-transparent or opaque when another input and enable input is not associated. When several transparent latches follow each other using the same enable signal, signals can propagate through all of them at once. However, by following a transparent high latch with a transparent low or opaque high latch, a master-slave flip-flop is implemented. This is one of the different types of flip-flops that I was talking about. The gated SR latch. A synchronous SR latch, sometimes clocked SR flip-flop, can be made by adding a second level of NAND gates to the inverted SR latch or a second level of AND gates to the direct SR latch. The extra NAND gates further invert the inputs, so the simple SR latch becomes a gated SR latch, and a simple SR latch would transform into a gated SR latch with inverted enable. With E high enabled true, the signals can pass to the input gates to the encapsulated latch, all signal combinations except for 0, 0, hold, equals, hold, and then immediately reproduce on the QQ output. The latch is transparent. When E is low, enable false, the latch is closed or opaque and remains in the state it was left the last time E was high. The enable input is sometimes a clock signal, but more often a read or write strobe. When the E is low, enable false, so basically the latch is opaque, and it remains in the same state as the last time he was high. The enable input is sometimes clock and sometimes strobe. This is the gated SR latch. As you can see, it consists of three inputs R, E, and S, and the outputs are Q and Q0. The gated SR latch circuit diagram constructed from AND gates and NOR gates. So these are the first two gates are AND gates and the other two are NOR gates. And when E is low, the latch is closed or opaque, and it remains till the last time E was high. Next is the gated D latch. This latch exploits the fact that in the two active combinations 0, 1 and 1, 0 of a gated SR latch, R is the complement of S. The input NAND stage converts the two D input states 0 and 1 to these two input combinations for the next SR latch by inverting the data input signal. The low state of the enable signal produces the inactive 1-1 combination. Thus, a gated D latch may be considered as a one input synchronous SR latch. This configuration prevents application of the restricted input combination. It is also known as transparent latch, data latch, or simply gated latch. It has a data input and an enable signal, sometimes named clock or control depending on the situation. The word transparent comes from the fact that when the enable input is on, the signal propagates directly to the circuit from the input D to the output Q. Transparent latches are typically used as I/O ports or in asynchronous systems or in synchronous two-phase systems. Synchronous systems that use a two-phase clock, where two latches operating on different clock phases prevent data transparency, as in a master-slave flip-flop. Latches are available as integrated circuits, usually with multiple latches per chip. For example, 74HC75 is a quadruple transparent latch in the 7400 series. This is one of the most common quadruple transparent latches. This is the image of a gated D latch, and a gated D latch based on SR NAND latch. So as you can see, D and E are the inputs and Q and Q0 are the outputs. It's basically on a NAND gates and AND gates. Next, we'll discuss about the Earl latch. The classic gated latch designs have some undesirable characteristics. They require double rail logic or an inverter. The input to output propagation may take up to 3 gate delays. The input to output propagation is not constant. Some outputs take 2 gate delays while others take 3. Some outputs take 2 gate delays and some outputs take 3 gate delays, and it all depends upon the situation. It's based upon the gate delays. Designers look for alternatives. A successful alternative is the Earl latch. It requires only a single data input and its output takes a constant 2 gate delays. In addition, the 2 gate levels of the Earl latch can, in some cases, be merged with the last 2 gate levels of the circuits driving the latch, because many common computational circuits have an OR layer followed by an AND layer as a last 2 levels. Merging the latch functions can implement the latch with no additional gate delays. The merge is commonly exploited in the design of pipeline computers, and in fact was originally developed by J.G. Earl to be used in the IBM System 360 Model 91 for that purpose. The Earl latch is hazard-free. If the middle NAND gate is omitted, then one gets the polarity hole latch, which is commonly used because it demands less logic. However, it is susceptible to logic hazard. Intentionally skewing the clock signal can avoid the hazard. This is a picture of the Earl latch. Earl latch uses complementary enable inputs: enable active low EL and enable active high EH. So EL is the enable active low and EH is the enable active high. These are inputs, complementary inputs. Classical positive edge triggered D flip-flop. This circuit consists of 2 stages implemented by SR NAND latches. The input stage, the 2 latches on the left, processes the clock and data signals to ensure correct input signals for the output stage. The single latch on the right. If the clock is low, both the output signals of the input stage are high, regardless of the data input. The output latch is unaffected and it stores the previous state. When the clock signal changes from low to high, the only one of the output voltages, depending on the data signal, goes low and resets the output latch. If D equals 0, the lower output becomes low. If D equals 1, the upper output becomes low. If the clock signal continues staying high, the outputs keep their states regardless of the data input and force the output latch to stay in the corresponding state as the input logical 0 of the output state remains active while the clock is high. Hence, the role of the output latch is to store the data only while the clock is low. The circuit is closely related to the gated D latch, as both the circuits convert the 2 D input states 0 and 1 to 2 input combinations 0, 1 and 1, 0 for the output SR latch by inverting the data input signal. Both the circuits split the signal D signal in 2 complementary S and R signals. The difference is that in the gated D latch, simple NAND logical gates are used, while in the positive edge trigger D flip-flop, SR NAND latches are used for this purpose. This is the difference between gated D latch and edge triggered D flip-flop. The role of these latches is to lock the active output producing low voltage or logical 0. Thus, the positive edge triggered D flip-flop can also be thought of as a gated D latch with latched input gates. This is an image of the classical positive edge triggered D flip-flop. It's made of SR NAND latches. Next, we move on to the master-slave edge-triggered D flip-flop. A master-slave D flip-flop is created by connecting 2 gated D latches in series and inverting the enable input in one of them. It is called master-slave because the second latch in the series only changes in response to a change in the first master latch. For a positive edge-triggered master-slave D flip-flop, when the clock signal is low logical 0, the enable seen by the first or master D latch with the inverter clock signal is high logical 1. This allows the master latch to store the input value when the clock signal transitions from low to high. As the clock signal goes high, 0 to 1, the inverter enable of the first latch goes low, 1 to 0, and the value seen at the input to the master latch is locked. Nearly simultaneously, the twice inverted enable of the second or slave D latch transitions from low to high, 0 to 1, with clock signal. This allows the signal captured at the rising edge of the clock by the now locked master latch to pass through the slave latch. When the clock signal returns to low 1 to 0, the output of the slave latch is locked and the value seen at the last rising edges of the clock is held by the master latch begins to accept new values in preparation for the next rising clock edge. By removing the leftmost inverter in the circuit at side, a D-type flip-flop that strobes on the falling edge of the clock signal can be obtained. This is the image of a master-slave edge triggered D flip-flop. This is a negative type D flip-flop. Next, we move on to timing parameters. The input must be held steady in a period around the rising edge of the clock known as the aperture. Imagine taking a picture of a frog on a lily pad. Suppose the frog then jumps onto the water. If you take a picture of the frog as it jumps into the water, you will get a blurry picture of the frog jumping into the water. It's not clear which state the frog was in. But if you take a picture while the frog sits steadily on the pad or steadily in the water, you will get a clear picture. In the same way, the input to a flip-flop must be held steady during the aperture of the flip-flop. Setup time is the minimum amount of time the data input should be held steady before the clock event, so that the data is reliably sampled by the clock. Hold time is the minimum amount of time the data should be held steady after the clock event, so that the data is reliably sampled by the clock. Aperture is the sum of setup and hold time. The data input should be held steady throughout this time period. Recovery time is the minimum amount of time the asynchronous set or reset input should be inactive before the clock event, so that the data is reliably sampled by the clock. The recovery time for the asynchronous set or reset input is thereby similar to the setup time for the data input. Removal time is the minimum amount of time the asynchronous set or reset input should be inactive after the clock event, so that the data is reliably sampled by the clock. The removal time for the asynchronous set or reset input is thereby similar to the hold time for the data input. Timing parameters again. Short impulses applied to asynchronous inputs, set and reset, should not be applied completely within the recovery removal period, or else it becomes entirely indeterminable whether the flip-flop will transition to the appropriate state. In another case, where an asynchronous signal simply makes one transition that happens to fall between the recovery removal time, eventually the flip-flop will transition to the appropriate state, but a very short glitch may or may not appear on the output, depending on the synchronous input signal. This second situation may or may not have significance to a circuit design. Set and reset and other signals may be either synchronous or asynchronous, and therefore may be characterized with either setup, hold or recovery removal times. And synchronicity is very dependent on the design of the flip-flop. Differentiation between setup, hold and recovery removal times is often necessary when verifying the timing of larger circuits, because asynchronous signals may be found to be less critical than synchronous signals. The differentiation offers circuit designers the ability to define the verification conditions for these types of signals independently. So I would like to conclude my lecture on flip-flops here, and I thank you for watching this video, and I request you people to kindly subscribe to this video. Thank you.